This is my last video on exploring suppose exponential and logarithmic growth models and searching for unknowns given certain parameters to begin with, or knowns. But in the last video we had talked about exponential growth and decay models, and then there was this third logistic growth model, which is this one right here. What I'm going to tell you is, and this is probably great news for you, you don't have to memorize what this model looks like. You certainly need to know that continuous growth is modeled by y equals an initial amount times e to the rate times time. You need to know that. But this logistic growth model, like you see here, is likely going to be something that's given to you. And in this case, it's certainly one that I am giving to you. So let's take a look at how this modeling situation works and how we can look for some unknowns. By reading it first, we see that on a college campus of 5,000 students, we have 5,000 total students. It says one student returns from vacation with a contagious and long-lasting flu virus. Thank you, one student. So it says the spread of the virus is modeled by this equation right here. So let's take note of what these values are. We say y is the total number of students affected and t is the number of days. So when we look at this, we say the day number, we can look at that, and then we have the number of infected is the output for this function, or our y values there. So it's good to know, and we don't have to take a look at the graphs, but when you do, what you'll see is a situation where it's going to go up to 5,000 is the fun thing about these logistic growth models. We have a situation where as the time flows, we have one student being sick here at time 0, and it grows really quickly, and then it kind of goes up and it approaches 5,000. And the reason why it grows so quickly is because everybody's getting everybody sick, but after you get close to 5,000, it tends to level off. And you can't have more than 5,000 sick, so that exponential growth kind of tends to level off. So we say y is the total number of students affected after t days. Let's take a look at this. It says the college will cancel classes when 40% or more of the students are infected. So let's start with this first question. It says how many students are infected after 5 days? Well, the nice thing is we have this model and we've been given a time. So using this time, we're going to substitute this time in for this t, and you can see that it's really the only quantity we don't know. We could go solve for the number of infected students after 5 days. So we're going to go ahead and just plug this in. We say y, when x equals, or t equals 5, we say y equals, now we have 5,000. And this is over, now all in parentheses, 1 plus 4, 9, 9, 9, e to the negative 0.8 times the time, which in this case is 5. And I'm going to put this in parentheses and so with that also as well with it. So we'd say, looking at this, the hardest part really is going to be punching this all into a calculator. So maybe we type this all in at once. If we were ambitious, we could say 5,000 divided by, now all in parentheses, we have 1 plus our 4 with 3 nines, and we say e to the power of, so I have e to the power of negative 0.8 times 5. I'm going to end cap that one there, and I need another end parenthesis because this part right here, that end parenthesis matched up with the beginning of our exponent here. So when I hit enter, we could say, well, they're going to be about 54.02 students sick. So I'm going to say 54.02, and we want to make sure we label this. Okay, you're going to get graded on putting your units on there. So we say 54.02 students, and yes, remember that this is just a model. I mean, it's not really going to tell us exactly how many students will be sick, but approximately how many. So now here comes this question. After how many days? How many days? Go find the time. Will we cancel college classes? Well, the weird thing here is, remember, if I want to find the number of infected, I need to know the number of days, and that was what we just did. Now I'm trying to find the number of days, and I need to know the number of infected before I can tell you this. So the key to this problem is this statement right here. It says when 40% or more of the students are infected. So we need a number of students here. We need to know, what is 40% of the student population. And what we know is we already have 5,000 students. So really we need to find 40% of 5,000. That would be the number of students we would need before we shut down the campus, and that's what we'll plug in for y. So to find 40% of a number, we just multiply that number by 0.40, or 40% as a decimal. We'll get our calculators out and we say 0.40 of 5,000. 40% of 5,000 comes out to be 2,000. So we have this. We have 2,000 students. We're going to shut down the campus if it's over 2,000. So now using our model, we say we'll plug in 2,000 for our model here. And this is equal to now this really fun expression, this 5,000 over all in parentheses 1 plus 4, 9, 9, 9, e to the negative 0.8 times time. So this tends to be a struggle algebraically for a lot of people. So what I'm going to do is I'm going to give you some suggestions. When you're solving, of course, a rational expression here for something in the denominator, okay? Or at least, let's start with this. When we're solving an exponential equation, what we're going to need to do is isolate the base. But because that's in the denominator and I have this rational expression, what I'm going to do is I'm going to reciprocate both sides of this equation. And this is a really quick way of getting around what we're going to have to deal with here. But I have 1/2000th, and this would be 1 plus 4, 9, 9, 9, e to the negative 0.8 time, all over 5,000. Thing is, now that we've gotten this base out of the basement, we can start to work on isolating a little bit more. So we're going to multiply both sides by 5,000, which is really 5,000 over 1. So on the left side, we get 5,000 over 2,000, which is 5 halves. On the right side, we have this 1 plus 4, 9, 9, 9, e to the negative 0.8t. So again, we're trying to get this by itself. We should probably subtract 1 from both sides. And, 1 whole is the same as 2 halves. So 5 halves minus 2 halves is 3 halves now on the left. And this is equal to 4, 9, 9, 9, e to the negative 0.8t. And because I know 3 halves is not, wicked as a decimal, what I'm going to do is this. I'm actually going to trap this off here. Divide both sides now by 49.99. And I'm going to do this with the decimal on the left. So if we get our calculators out here, we'd say 3 halves. First of all, 3 halves is 1.5. And we're going to divide that by 49.99. I'm going to leave that up here. But we end up with this. Actually, I need this number. 3.0006 times 10 to the negative 4. So really this is a very small number. We're going to write this out here. We get 3.0, let's write that out. 3.0006 times 10 to the negative 4 would mean move our decimal back 4 places. We have a 0, a 0, a 0 here, and then a 0 there. We really get 0.00030006, and this is equal to now negative 0.8 times the time. So now all we need to do is divide, well actually no, not divide. We have e to the power of this. Apologize. We divided by the 49.99. So now we need to rewrite this in logarithmic form since we have that base isolated. So we said log base e of, now here's the thing, all of this turned into this. So we say of 0.003006, and this would be equal to now negative 0.8 times the time. So we'll divide both sides now by negative 0.8. So now, let's get our calculators out and try to work with this here. We had log base e of this, which is really my answer right here. If we're going to take the log base e of that, and let me check this out here. That divided by that. Okay, so we had scientific notation. I was wondering why it wasn't 3.006 because we had times 10 to the negative e. So we're going to take now our ln of our answer. Remember your answer key is behind your negative key here. ln of our answer, and we're going to divide that in parentheses by 0.8 negative, and this should give us the time. Now the time would be about 10.14. So we have time is approximately 10.14. And in terms of units of time, this is in days. So we're going to label this in days. So it would take about 10 days before the school is going to shut down the campus, but that's the same as saying it would take about 10 days in terms of the time here for the population to be 2,000. Cheers.